First, we're going to look at the effect of typical implementation latency on feedback between players. This means that there is no synthetic latency added to the network yet. Also, we're not compensating for the latency yet, just directly rendering the last received position. After we build up speed, we will try to drive right next to each other in formation. This means that each player will constantly adjust to the other player's position on his screen. Positions remain relatively accurate at low speeds, but as we go faster, the discrepancy will increase. As we saw in our testing videos, even a small time difference can mean a large position difference at high speeds. So now when we try to get in formation, we are adjusting to inconsistent representations of each other's positions. These incorrect adjustments propagate through the feedback, and this leads to instability. Both cars begin to slow down, sometimes with growing oscillations. This completely destroys the feedback between the players, and the game becomes unplayable. Now let's look at what happens when we inject synthetic latency. Here we'll insert 410 milliseconds round trip, which corresponds to the 95th percentile of 4G. Since we are adding additional latency here, the effects will be much more pronounced. To test the effects, we'll first build up some speed, and then try and get in formation with each other. Even at low speeds, positions have already diverged significantly. And again, as we speed up, this discrepancy will grow. Each player thinks that they are in first place in their own screen. Now if we try to get in formation, each player has to slow down dramatically to let the other player catch up. This is an example of runaway feedback destroying the interaction between the players. The game comes to a grinding halt as each player tries to adjust to the position of the other. This renders highly interactive play impossible. Now we'll turn the compensation on and increase the latency up to 600 milliseconds round trip. This corresponds to the 95th percentile of 3G and public Wi-Fi networks. At low speeds, positions remain consistent. Here again we'll try and build up some speed and then get in formation to test the compensation. Not only are positions synced, but the actions of the player on the right are showing up immediately on the left player's screen. We are able to comfortably maneuver around each other without the risk of artificial collisions like we saw in our latency testing videos. This accurate sync allows us to build highly interactive and precise maneuvers into the game design, like drafting for example. To draft, the player on the right tries to stay directly behind the other vehicle, on top of the yellow sweet spot. Depending on how close they stay to the sweet spot, the players can achieve up to a 15 mph boost. Not only are players adjusting to each other's positions constantly, they're also constantly adjusting to the dynamic drag forces in the game. We can see that the compensation can handle finely tuned maneuvers, but what about something with a little more dynamic range, like a slingshot? To slingshot, the player on the right steers around the player on the left and back in front of him into drafting position. The player on the left can then perform another slingshot for an additional speed boost. Players can constantly be maneuvering and interacting with each other on a much higher level than other games. The ability to build highly interactive features into a game allows developers to deliver an experience that is more fun for the players. Let's say at this point the end of the race is approaching, and the player on the right wants to defect on the player on the left so he can win the race for himself. The player on the right can try and sneakily come up behind the player on the left and make him spin out. And if that doesn't work, he can try bashing him into the wall. Since game states remain consistent the whole time, not only is the game more fair, it allows for more interactive and fun features in the game design. We've seen that the compensation can handle high static latencies, but let's see how it would perform when the network is affected by something like a channel fade. To test this, we'll introduce a periodic two-way channel loss of 600 milliseconds and set constant latency to 410 milliseconds. This means that the compensation must now handle 500 milliseconds of prediction horizon on each side, 1000 milliseconds round trip. In current games, when this size of fade occurs, you lose the connection and have to go all the way back to the lobby. You lose all game progress and it takes minutes to get back into a new game session. We can see the positions remain completely consistent and maneuvers still show up immediately on the other screen. This precise sync again allows us to perform collaborative and competitive maneuvers. Even when affected by something like a channel fade, the compensation maintains a tight feedback loop between the players. This robustness allows for a compelling and fun gaming experience, even with an awful network connection.